Okay, as you look at these two functions, that one and that one, they look kind of different, obviously. One of them has a whole bunch of terms and one of them has a single term. But the term that is there is included in both of them. So there's a bunch of extra terms here. What we're going to look at trying to do here is show that for small values of x, they're quite different. But as soon as you make x really large numbers, they're almost identical. It's hard to maybe see it just by looking at the two functions, but maybe think about what happens as you put numbers in there. We're going to use a table first. I know I didn't put solve numerically, but we'll look at it numerically here, which means making a table. So putting those two functions in. One maybe is tedious. Perhaps we'll even... I forgot the 5 here. Yeah, we got plus 6. The other one's easy, of course. 3x power of 4. Now we're going to look at the table first because I think it might give you some insight here. And I don't want to just look at I guess we'll start by looking at it just automatically filling out the numbers 1, 0, 1, 2, 3, 4. Okay, so before we look at the graph, I think you might get it more from the table here. Okay, so there's the table. There's a table that goes x changing by 1 each time. What's happening with these values here? We got 6 and 0. We got 5 and 3. 5 is almost twice as big as 3. We have then 40 and 48. Right now it's smaller. Okay, then we got it smaller again here. But as you go, I know that if you think in terms of how the difference between them, these are 2 different, but these are 8 different. So it might sound like, well, wait, they're getting farther apart. But relative to the size of them,
how do you get y2?
I put in both functions here, 3x to the 4th, and then we're comparing those two, right?
Quiet, Boaz.
Okay, so I just set up the table to change by 1 at a time here. If you scroll down here, 5 and 3, one's almost twice as big as the other. Is that still true down here? Is this one twice as big as that one, or half as big? Not, right? They're relative to their size, they're actually getting closer together here as you go, right? If you get up to bigger numbers like this, 41,000, 43,000, okay? If the farther you go here relative to their size, they're closer and closer together here. Now we're only up to x equals 22, right? At 143, they still, you push the button how many times? So maybe, now, don't forget, now we're looking at, this is starting to be scientific notation here, but they're starting to get closer and closer to being the same thing. As you get bigger and bigger, as you make x bigger and bigger, 6.94, 6.83, they're both times 10 to the 6th. Relative to their size, they're getting closer and closer here. 1.44, 1.46, it's in the 3rd significant digit now. Before it was in the 1st. So we understand here the concept. I'm going to go back to the table then and make it so I can enter my own numbers here. If you enter your own numbers, so at 1 and then maybe at 10, at 100, at 1,000, if x is 1,000, at 1,000, it shows them, it rounds them up as being the same. There, 1 is 3 with 12. 3, trillion, I guess. This is almost 3 trillion, right? It's 2.998 trillion. If you went to the next one here, which is 10,000.
Can we get to a Google?
This calculator can't comprehend that. It's adding an extra 9 here. The farther that you go, the closer these are, right? This is 3 times 10 to the 16th. This is 2.9998. So if you keep making x bigger and bigger, they're essentially becoming the same number. Why does that happen? This one has all these extra terms. This is the question here, is why does that happen? If you look back at the functions here, I mean, put in whatever number you want. Put in a bigger number. I'll continue with my pattern here. You know, you notice the pattern here, it's just 2.8, it's adding a 9. So it's making it, you know, kind of 10 times closer every time there. 3 times 10 to the 20th, 2.99998 times 10 to the 20th. The larger you make x, the closer they are. So what we're saying is, as you make, I mean, absolute value, because we could have done the same thing with negative x values. If you put in negative x values, so all this absolute value means is large positive or negative numbers. Positive or negative x values. It's hard to see on the graph. I'm actually going to change this to solve numerically. But you could draw the graph as well. You could show that the lines kind of start to get closer and closer to each other as you do that, which we will do in a second. I guess you'd have to cross that out, but I want to put a graph and this table and stuff here. Maybe this table or whatever other table you had. This is not the best table to show this, but it's good enough. Okay, they're quite different. Relative to the size of them, they're quite different when they're small. But when you get up to here, even before that, they're getting closer and closer together. They're getting relatively the same, you know, they're virtually identical. Or in other words, the limit of each one, what's the limit of each one if we keep making x bigger and bigger to the right? If we make x, as x approaches infinity of each one, like if we talk about the limit as x approaches infinity of f of x, and we talk about the limit as x approaches infinity, so if we're making x bigger and bigger of g of x, what's the limit as you approach infinity of each of those? What happens to these values? If I kept going here and making this bigger than 100,000, make it a million, a billion, a trillion for x, what's going to happen with these values? Are they going to level off? No, they're getting bigger and bigger, right? If you raise this number to a bigger and bigger power, it's just going to be getting bigger and bigger. So the limit here of each of these is infinity. Okay? But the fact is, what's the ratio of the two of them? The limit of the ratio of the two of them, which means if I divide the two of them, f of x divided by g of x, if I divided those numbers that are getting closer and closer to being equal, if I divide them, what's the limit of that ratio? It's 1, right? This is 1. This is the key here. We are going to talk about an end behavior model, which means a simpler function that has the same behavior as you go to the right or the left. That's what this means. All right, so it says, I mean, it's written down here. You don't have to rewrite it, but the function g is a right end behavior model for f if and only if that limit of that ratio is 1. So the limit of the ratio, okay, limit of ratio of the two of them, because they're getting closer and closer together. Okay, it's an end behavior model, means it behaves the same way. It's a simpler function that has the same behavior as you go to the right or the left. And then, of course, you can talk about a left-end behavior model. If that ratio, as you approach negative infinity, that's the key, right? As you go to the left, if it equals 1. Same thing, though. They're going to have to be. I mean, we're leaving it broad for other reasons, I guess, but when you look at polynomials, which of the terms here was the one, like, I mean, I guess another way to think about it here is, which of the terms in this thing is the kind of the dominant term as you get bigger and bigger? Yeah, this is the dominant term as you make numbers bigger and bigger. If you're raising something to the fourth, that's going to get large a lot quicker than raising something this, right? We're going to have to pause this and then we'll talk about that because it's important to realize what happens there.